I'm feeling literally honored. I always wanted to say that. I'm actually honored too. Thanks to Eleanor and Gina and Joan, and especially to our unbelievably energetic impresario, Hilda, for putting this together. I switched from the math department to the statistics department at Stanford as a student in the fall of 1961, helping both departments, as the old joke goes, and that makes it 50 years in statistics, and that was probably the best decision I've ever made to make that change. There's a lot of fields these days that like to push data around, but statistics is still the only field that takes inference seriously. There's two main schools of inference, the Bayesians and the frequentists, and my book went on and on about the relationship between the two, and then I've continued thinking about it, and that's what I'm going to talk about today. The advent of large-scale inference problems has put pressure on both philosophies, and I think that's a subject that will keep on growing, the subject being trying to connect the two. So, let's see here. There we go. This has been a hot century for applied Bayesian statistics, particularly as implemented by MCMC, the hottest topic of all in that area. And today I'm going to go retro back to an older method of getting Bayesian posterior inferences, importance sampling. And an important paper here is by Newton and Raftery in 1994, JRSSB. It's one of those discussion papers. And they use a non-parametric bootstrap as a basis for doing importance sampling to get posterior distributions in Bayesian problems. And today I'm going to go, it's a very nice paper, but their timing was bad. MCMC was just really getting going, and the discussion from the MCMCers is pretty hostile if you go and read the, not nasty, but why do importance sampling when you have this wonderful new tool? But I like importance sampling, and today we're going to go parametric bootstrap and importance sampling for Bayesian inference. By going parametric, you get certain advantages in actually doing the calculations, but also, and this is a point that I'm really interested in, is that you learn something about the relationship between Bayesian and frequentist inference, and that's what I'll be working toward. And that particularly applies to the kind of objective Bayesianism in which you start with vague priors, uninformative priors. That's the main, when I said the Bayesian inference, applied Bayesian inference is a hot topic these days, it's really, what I really meant was that objective Bayes inference in which you start with priors that don't reflect prior experience, but rather mathematical properties. And that I think it's particularly important to connect. So here's a simple example that I'll carry through for a while. 22 students taking 2 tests, mechanics and vectors. It's from Marty Kent and Bibby's book. the data, each student presents a bivariate data vector, y, the mechanics and the vector scores, and then the whole data set, boldface y, is a 22 by 2 data matrix, 22 students, 2 measures on each, and I'll take as a parameter of interest the actual correlation between mech and vec, and the sample correlation is 0.498. Theta hat is 0.498, and we wonder how accurate that is. Here's the 22 students graphed out. And incidentally, there's 88 students, but I took a random subset of 22 of them. And this problem of inference for theta hat was solved in 1915. So that got Fisher's name up here. This is Fisher's first paper in statistics, in which he solved the problem of getting the density of theta hat, the sample correlation as a function of the true correlation theta, and I just wrote the function there because it's pretty horrible. There's many forms of it, all look pretty bad, but these days, of course, it's a microsecond to actually calculate it for any one case. This assumes the points are bivariate normal. The sample from bivariate normal distribution, normal to mu sigma, mu being the mean vector, sigma the covariance matrix. And Fisher also provides us with a confidence interval. Theta is between 0.084 and 0.754. That's 95% confidence, 2.5% non-coverage in each direction. This picture is one that Fisher would have loved to see, but it would take them an awful long time to compute in 1915. The black curve here is the density, Fisher's density function for the correlation f sub theta of theta hat, assuming that theta hat is that theta is actually 0.498. So in this sense, Fisher's curve is a parametric bootstrap, in the sense that it's the density we'd see if the unknown parameter equaled the MLE. And it was really hard to calculate this in 1915, but it's a billionth of a second now. Well, that's not quite true, a second. A thousandth of a second. But if these days, what was the hard part was getting the theory for the curve. But these days, by brute force, we can work our way around that and not have to use our brains to get the theory. We can use our computers to brute force out the numbers, and that's what the green histogram is. The green histogram is a parametric bootstrap directly aimed to get this curve. So we assume that we have we're using a bivariate normal model, yi independent normal mu sigma. We estimate mu by mu hat and sigma by sigma hat by MLE. And then a parametric bootstrap sample, we take yi star independent normal mu hat sigma hat for I equals 1 through 22. That gives the boldface y star there is a bootstrap data set. We can take its correlation, theta hat star. In an excess of enthusiasm, I did 10,000, which just meant I held down the key a little longer than I needed to. And that only took about 3 seconds. And so now I have 10,000 theta hat stars, and I could, and that's what this curve histogram is. And you can see Fisher was right. It fits the curve. The standard deviation of those 10,000 numbers is 0.168. That would be a bootstrap estimate of standard deviation or standard error. But we might, we're after a bigger game. We want confidence intervals. So one thing we might do is just use the 2.5 percentile and the 97.5 percentile. That's 0.109, 0.761, which really isn't awfully close. It's close, but not awfully close to the better Fisher numbers. And there's a reason it's not so great. You can do better by reweighting the 10,000 numbers. This is a method called BCA, bias corrected and accelerated, but I won't harp on the details. The basic idea is that those two numbers I told you before, 0.109, for example, is the 2.5% unweighted percentiles of the 10,000 numbers. That is, it's the 250th smallest one. The idea of the BCA method is if you change the weights on the points in a certain way, you can get better confidence intervals. You get second-order accurate intervals that are really usually very accurate. And I've written a formula for the weights. The main point is that the weights aren't all 1 over 10,000. They're different weights, depending on a couple of extra things you calculate. Now I have my 10,000 points, but I also have different weights on them. And if I take the 2.5 percentile weighted, that is 0.075 there in the red box, has 2.5% of those weights to the left of it. 0.748 has 2.5% to the right, and that's much closer to the exact numbers. Not an accident. And of course, we don't need it here because we have the exact answer. But if I use a different statistic, I can keep doing the BCA method, but I won't have Fisher around to solve the problem for me, theoretically. Okay, so now on to the key moment here, where we get to the Bayesian connection. Now, if we're going to be Bayesians, we have to have a prior pi of theta. And let's say we have some parameter we're interested in, t of theta. Could be theta itself in this case, or could be theta squared, or e to the theta, or anything you wish, t of theta. And the top green line there is Bayes' rule. The expected value of t of theta given theta hat is the ratio of two integrals. The integral of t of theta pi of theta, f sub theta hat d theta, divided by the integral of pi of theta, f sub theta hat d theta. Notice that theta hat is fixed here. F sub theta hat is the likelihood, how f sub theta hat changes with theta hat fixed and theta varying. And it's the fact that the integrals are with respect to a likelihood that makes Bayesian computation sometimes quite difficult. And the idea of importance sampling is to change it from a likelihood to a regular probability density. And the conversion factor there is the ratio of the likelihood to the bootstrap density. It's in the red box. Capital R of theta, f sub theta hat, the likelihood in the numerator, f sub theta hat of theta, the bootstrap parametric density in the denominator. I've quit using theta hat star. Theta just stands for any point in the theta space. If I use theta hat star, that starts looking messy on the. So this R of theta is a quantity that's supposed to convert likelihood into a parametric bootstrap density. And then in the top green line, if you divide and multiply by f sub theta hat of theta, you get the bottom green equation. The posterior expectation t of theta given theta hat is the ratio of two integrals, integral in theta, integral of t pi r f sub theta hat of theta in the numerator, integral of pi r f sub theta hat of theta in the denominator. And the advantage here is that what we're doing then is integrating with respect to a density. Each one of these can be done now by importance sampling. That is, this is just using a ratio estimator in the usual way. So here's the usual way. We draw B, I've called it capital B, observations from the parametric bootstrap density. F sub theta hat theta 1, theta 2 through theta b. In my case, it was 10,000, and the thetas were these theta hat stars. They were bootstrap correlation coefficients. And now, for each one, we take ti, t of theta I, pi of theta I, ri, r of theta I, and then in the red box is the importance sampling estimate of the posterior expectation. I've called it E hat of t of theta given theta hat. Is just a ratio of two sums, summation ti pi I ri over summation pi I ri. And all we've done is put weights, just as in the BCA method, but now different weights. Now the weights on theta I are pi I ri. And we've reweighted, and now we take the averages. And we know that this is going to work from classic importance sampling theory. We know that E hat's going to converge to E as B goes to infinity, and later we'll see that I've chosen B much too big. So what about this prior density? Where did this come from? Well, this brings me to Jeffreys, Harold Jeffreys, the R.A. Fisher of Bayesian, of objective Bayesianism. And Jeffreys, following a long line of tradition going back to Laplace and Bernoulli, wanted to find uninformative prior distributions, distributions you could use when you didn't have prior information. That is, it says somewhere that Jeffreys was the first real Bayesian because he was the first person who could use Bayes theory all the time. Well, he wasn't the first, but he made the story better. Laplace always chose thetas, prior pi of theta, flat priors equal, and that brought a lot of criticism from people like Fisher, who said, well, if theta's flat, what about e to the theta? Shouldn't that be flat prior? Jeffreys answered this by having a formula of invariant priors. It's in the box there for our p parameter family. The Jeffreys invariant prior, pi of theta, is proportional to Fisher, to the 1/2 to the square root of the determinant of Fisher information matrix. Which sounds exotic. In one dimension, all it means is that pi of theta is 1 over the standard deviation of the maximum likelihood estimate. So you're adjusting the range by the standard deviation. In the normal correlation case, the answer is pi of theta equals 1 over 1 minus theta squared. That's Jeffreys invariant prior. And for various reasons, I'm going to emphasize the Jeffreys prior. There's lots of other uninformative priors that people use these days, but this one makes the talk go easier. So here I did this. I did this all. This is for the student score correlation. I did the 10,000 theta hat stars. I'm just calling them theta 1 through theta I through theta b. And the red dashed line is the histogram, a smooth histogram, of the 10,000 theta i's unweighted. That is, with equal weights, 1/10,000th on each one. So I could have drawn a histogram, but I've made it smoother. The black curve is the posterior distribution of theta given theta hat for the student score data using Jeffreys prior. That is, I use that formula what I've done is reweight the 10,000 points with respect to the weights pi I ri, where pi I is 1 over 1 minus theta I squared, and ri is that conversion factor we had before, which I got numerically. And you can see that the black curve is shifted a little left of the raw numbers. The weights are higher on the left than on the right, and that shifts things. The green curve is the BCA curve, and you can see that things work out just about right here. And it is known that Jeffrey's method gives good frequentist confidence intervals. That is, Jeffrey's prior, in this case, gives good frequentist confidence intervals, same as the BCA method. What do I mean by in this case? I mean for one-dimensional problems with no nuisance parameters. Things get much more difficult as we get into the higher dimensions. Well, of course, today we're thinking of higher dimensions, meaning thousands. But right now, I'm just going to go from 1 to 5, and we'll see that things get harder. So, multiparameter exponential families in p dimensions. So, a very brief moment on exponential families. We're going to have a p-dimensional sufficient statistic that I'll call beta hat. And usually beta hat is gotten by sufficiency reduction from some bigger data set. And we have some p-dimensional parameter vector beta, which is the expected value of beta hat. And just to fix ideas for the Poisson, written in the usual way, e to the minus lambda to the x over x factorial. Beta hat is x, and lambda is beta. And now in the red box is the exponential family written in a perhaps not familiar way that I usually attribute to Hufting. F sub beta of beta hat, the density is F sub beta hat of beta hat, e to the minus d beta hat beta over 2, where d is the deviance. It's a definition of the deviance is given below. In a normal family, that would just be square difference, multidimensional square difference. So this is a nice form for exponential families. Beta, if you want to find the maximum likelihood estimate, it's beta hat. That makes f sub beta of beta hat as big as possible. Remember, beta hat's fixed. And then the density, the multidimensional density, falls off from the maximum according to e to the minus d beta hat beta over 2. Kullback-Leibler distance, 2 times that. So that makes for a very pleasant picture, I think. And the nice thing that happens, and the reason to bringing this up, is that in exponential families, that conversion factor takes on a very nice form. So remember, the conversion factor, R of B, is f sub beta beta hat over f sub beta hat of beta, the likelihood divided by the parametric bootstrap density, and beta hat is fixed. And in the red box, it says R of beta is nu of beta e to the delta beta, where delta is the deviance difference, d of beta beta hat minus d of beta hat beta over 2. That's a particularly nice smooth function. And nu of beta is the ratio of the maximized densities f sub beta hat over f sub beta beta. And it turns out that is asymptotically and quite accurately usually equal to 1 over Jeffrey's prior. A nice thing that happens. And the reason I'm emphasizing Jeffrey's prior today, just because it makes the talk easier. That means if you put in nu as the, if you put in Jeffrey's prior, it exactly cancels the nu inside the red box. And you're left with the fact that the crucial factor, weighting factor, Bayesian weighting factor, pi of beta r of beta, is just e to the delta beta, which is convenient. So here's an example, useful example, the multivariate normal. So we'll assume that the yi's are independent normal d dimensions mu sigma, and then delta has a particular form, and it looks horrible, But once again, you only have to do it once, and it's easy to calculate. And I'll take as my example now, instead of the correlation coefficient, I'll do the eigenratio, theta, the ratio of the largest eigenvalue to the sum of the eigenvalues for sigma in the student score case. In the student score case, the dimension's 2, so sigma is 2 by 2, and theta is that ratio, and theta hat, maximum likelihood estimate, is 0.793, and we wonder what's the confidence interval for it. And now, again, we're lucky we don't need Fisher here to figure out the answer, because you can't figure out the answer. There's no neat answer here in a formula, but the computer doesn't care. We start doing parametric bootstraps, yi star independent normal mu hat sigma hat for I equals 1 through n22. I do that as many times as we want. I did 10,000 again, and I got 10,000 bootstrap eigenratios. And so here's what happened this time, and it's a little different. It's a lot different, actually. So the red dash curve again is the smooth histogram for the 10,000 bootstrap thetas, eigenratios, just a smooth histogram. The black line is a smooth, and I didn't smooth enough, histogram if you do the Jeffreys weighting. That is, if you put weights e to the delta on each of the 10,000 points. The green curve is the BCA density using those weights, and you can see what happens. In this case, the BCA has shifted the interval, the whole posterior interval to the left by quite a bit. The confidence regions, the black triangles are the confidence endpoints, well, I should say credible endpoints for Jeffreys, and the green ones are for the BCA. And I'll tell you, the green, if you want accuracy, if you want frequentist coverage accuracy, you have to shift the interval to the left. And this brings up and the reason, there's a reason here. The eigenratio, the maximum likelihood estimate, is biased strongly upward. And if you want to get good coverage, you have to shift the interval down to the left of the apparent maximum likelihood estimate. And you'll notice that the green points are very much shifted to the left of the estimate, 0.793, which is the 792, which is the horizontal line. And this brings up a criticism of Jeffreys priors or other uninformative priors, which is that in multidimensional problems, they may give poor results for specific one-dimensional parameters of interest. And this is well known in the Bayesian literature, and people have tried to get better Bayes, better uninformative priors, better in the sense of better matching what you'd get from the frequentist coverage idea. And it's hard going. Reference priors, for example, are trying to do that. We can do this automatically with the BCA method here, the reweighting. And this is a schematic of what's going on. Schematic in the sense of my last example. They're supposed to be in 5 dimensions. I've put it in 2 dimensions. It's the black point at the middle, blacked out at the middle, is supposed to represent the original 5-dimensional sufficient statistic mu hat sigma hat. In the bivariate normal, there's 5 parameters, 2 means, 2 variances, and a covariance. The red points are supposed to be the bootstrap replications, the parametric bootstrap replications. I've only put 250 rather than 4,000, 10,000. And now, if you imagine weight 1/10,000th on each of those, then any expectation you get will be just just gotten by adding up those the statistic T of I with weights 1/10,000th. If you put e to the delta on that, you change from the frequentist kind of estimate to the posterior Bayes estimate. So that e to the delta is what does the trick in the, assuming you're starting with a Jeffreys prior. Okay. Prostate cancer study. Finally getting to something closer to large-scale inference. So this is one of my favorites for making these points. A nice study by Singh et al. In 2002. Microwave study, 102 men, 52 with prostate cancer, 50 healthy controls. 6,033 genes measured by microarray for each man, and a test statistic ZI for each gene, testing the null hypothesis of no difference between the healthy controls and the cancer patients. And so we have 10,000 of these test statistics, and of course the goal is to identify genes involved in prostate cancer. And here's the histogram of the green histogram is a histogram of the 6,033 Z values, and the histogram looks sort of normal, but if that black curve is the curve you'd get if all of the null hypotheses were true. That's exactly a normal 0-1 curve blowing up by 6,033. And it doesn't fit exactly. It's too low at the middle, too high at the tails. That's good. That means that some of the ZIs were big and far away from zero and maybe indicate something was actually going on so that the investigators didn't waste their time. The red curve is a better fit. I've called it log poly 4 for a reason that'll soon be obvious. So I'm going to do Poisson regression models. Remember, I want to do everything today is parametric, so I wanted to have a nice parametric model here. So in that previous slide, there's the histogram, and it's I'll tell you there's 49 bins in the histogram, and the height of bin J I'll call Yj. That's just the number of ZJs that fell in that bin. And the center of the bin, where you can see the little dashes at the bottom, I'll call Xj. And so Yj is the number of ZIs in bin J. Xj is its midpoint. And the models I'm going to take Yi independent Poisson mu J, Yj independent Poisson mu J, where log J is a polynomial in the bin locations Xj of degree m. This is an exponential family of degree p equals m plus 1. And the thing I called log poly 4 is actually the fourth degree one, m equals 4, the quartic one. And it turns out that if you let a to j be log mu j, that delta has a simple explanation. The key thing that I'm using, delta, has a simple formula in this particular case. It's particularly simple, a lot easier than the multivariate normal one. So I want to have a statistic theta, a one-dimensional statistic, just to use as an example. So we start out with, in the top there, I put the R call for what we want. GLM Y, that's the vector of counts. Poly X4, a fourth degree polynomial Poisson regression. That gives some mu hat J's. A nice smooth version of the mu hat J's. Basically what it does is draw a smooth red curve through the histogram. And I'll take as theta my parameter of interest, the false discovery rate at 3. The estimate of the probability that a gene is null given that its value z exceeds 3. And I've written the little formula there, 1 minus phi of 3, that's the numerator. That's about 0.001, capital Phi being the normal CDF, over 1 minus f hat of 3, that being a smooth, the smooth estimate of the CDF. And that turned out to be, with model 4, it said that FDR hat of 3 is 0.192, plus or minus question mark, question mark. We'd like 0.192 is sort of an interesting number. It's getting to the range where you might report that gene to Dr. Singh as being interesting, likely to be non-null. But you'd really like it to be smaller than 0.192 usually. 0.1 is better. And with some idea of its accuracy, you might feel either more or less optimistic about reporting this one. Well, we can just start out with the parametric bootstrap. We have our formula. Yi star now is Poisson, independent Poisson mu I hat, and that gives some mu hat I stars and theta hat stars. The false discovery rate at 3, estimated false discovery at 3 for the bootstrap data. And I did, in this case, 4,000 of them. It took 30 seconds. And everything worked out pretty neatly. In this case, there wasn't much difference between the red dashed line, again, is the smooth histogram for the 4,000 unweighted theta hats, thetas. They were just and that gives you a raw bootstrap estimate of a confidence interval by using its percentiles, for example. The black curve is the Jeffreys prior posterior distribution, smoothed, and it's not much different than the red curve in this case. And the green is the BCA, also about the same. And you might wonder why there's so little difference. They're shifted just a slight bit left from the raw one. You might wonder why there's so little difference between the raw bootstrap and putting these weights e to the delta on. And the reason is that e to the delta is not very correlated with theta in this case. And that's just what happens with a lot of multiparameter problems. You essentially get just the raw bootstrap answer if you use a vague prior. It doesn't make much difference whether you use the frequentist or the Bayesian answer there, as long as you use model 4. It makes a big difference whether you use model 4 or model 8. Mike Stein likes to say that choosing your model is a lot more important than choosing your philosophy. And there's some truth to that. Here the black curve is the unsmooth histogram for the posterior Bayes interval for FDR using model 4. Model 8 is shifted quite a bit to the left. That is, model 8, instead of fitting a 4th degree polynomial, fits an 8th degree polynomial. So why did I choose the 4th degree in the first place? Well, I ran AIC, and you can see what happened. Model 2, AIC is 142.6. Model 2 is quadratic. That just amounts to a normal translation model. Model 3 wasn't any better. Suddenly you go to Model 4, you get a terrific drop in the AIC, but that's the lowest you ever get. The others aren't much worse, though. Model 8 is 75.6 compared to 73.3. I was a little suspicious of how well I was choosing model 4. So that's how I chose it. I thought maybe I'd been a little incautious. So I ran 4,000 bootstraps from model 8. And each time I did this first column and chose which was the best one from the AIC point of view. Model 2 and Model 3 were never chosen, but Model 4 was chosen 1,266 out of 4,000. Model 8 was chosen 22,050. So Model 8 was chosen more often. Those are the frequentest probabilities. We can change those to posterior Bayes probabilities by putting in that factor e to the delta for each choice. And that raised up Model 4 a little and lowered Model 8. 36% of the 4,000, the Bayesian estimate, posterior estimate for Model 4 was 36%. For Model 8 was 45%. So it certainly is no sure thing that Model 4 is right, but it's also no sure thing that Model 8 is right. What's clear is that model selection isn't going to be very stable in the database model selection here, and I'll get back to that point at the end of the talk. I wanted to talk about, before I do that, I wanted to talk about how big should B be. How many did I actually have to do? It says the internal accuracy. Because parametric bootstrap sampling is IID, that is, once you've chosen the parameters of the bootstrap from, everything just comes out, are sequentially independent of each other. You can use standard formulas to get their accuracy. And so the standard formula is in the red box, and down at the bottom there, for example, for Model 4, the Bayes estimate was 0.193 for theta hat. That's the Bayes posterior expectation. I believe the maximum likelihood estimate was 0.192. And that 193 was very accurate. The estimated coefficient of variation using usual sampling ideas was only 0.0019, which means that that 4,000 was an awful lot. If I went up to 100,000, it's not going to change very much. If I go to infinity, it's not going to change very much. And E hat is just about the same as E in this case, the actual posterior expectation. The same is true for Model 8. The E hat is 0.179, which is quite a bit less than 0.193, more in the direction we like, small, but its coefficient of variation is small too. So we know both those numbers quite well. What we don't know is which one we should use. But there's another kind of accuracy calculation that I think is more interesting, and that has to do with the sampling variability of Bayes estimates. How much would E hat T of beta given beta hat vary, not if we increase B, but if we got some new beta hats? Suppose we got another 22 students, or suppose we did the repeated things experiment with another 102 men. How much would we expect the Bayes estimate E hat T of beta given beta hat to vary? I.e., what are the frequentist properties of the Bayes estimates? And it seems like this, so a first level idea is, well, why don't we just bootstrap the bootstrap, do a second level bootstrap on top of the first one? And that sounds pretty hard because each one involves getting, say, 4,000 bootstrap replications. And if I bootstrap that, I've got a lot going. But there's a trick. I called it Bootstrap-after-Bootstrap. So we take the original ones. F beta hat gives beta 1 through beta B. In our example, B was 4,000, and the betas were each 5 or 8 dimensional, 9 dimensional, depending on which model we were using. And suppose we want bootstrap replications under some other value, gamma hat. I've just called it gamma instead of beta, so I don't keep using beta. And do we have to do the whole top line again? No. The answer is you can just reweight one further reweighting, and that's in the box at the bottom. There's some Q's that you calculate, and now E hat of t given gamma hat instead of beta hat is summation ti pi I ri qi over summation pi I ri qi. And there's almost no additional burden. Goes very fast. So then you get the bootstrap after bootstrap standard errors. In the top line here now, I've gotten a bunch more of parametric bootstrap replications. I've called them gammas, gamma 1 through gamma k. For each one, I do what I did on the previous page, call that E hat k. And then the standard error, the standard sample standard deviation of the E hat k's is the bootstrap estimate of standard error of E hat. And that can be applied to any of these Bayesian quantities that we've calculated. For FDR3, when I use model 4, the upper limit, which I think I forgot to say, of the 97.5% credible limit was, credible interval, was 0.241. And we might wonder how accurate that is. I applied this bootstrap after bootstrap, and the blue histogram, I did 400 second-level bootstraps. Each time got a 95% credible interval and kept track of the upper endpoint. And the blue histogram is the histogram of the upper endpoints. And 0.241 is supposed to say 0.241 there is in the middle. The bootstrap standard error for that was 0.03. So it's from a frequentist point of view, this number 0.241 is not so accurate. It's got a coefficient of variation about 1/8. From a Bayesian point of view, if you believe if you take the prior literally as being the truth, then it has no error. It's a fixed point of a probability distribution. So the points of view are quite different. I did one more of those that sort of shocked me. I went back to that table. Remember, we had a 36% chance of having model 4 and a 45% chance of having model 8. And I wondered how accurate those numbers were. And so I applied the bootstrap after bootstrap standard method. These are estimates too. And the 36% was 36% plus or minus 20%. Could have been 50, could have been 10. And the 45% was 45% plus or minus 27%. So in this case, really, even though those numbers like 36% and 45%, when they're just presented and you say those are the Bayes posterior odds, they look impressive. In fact, they have very little frequentist validity, and you're pretty sure that the whole thing was very sensitive and maybe not to be taken too seriously. So that brings us to the end of the talk. A few conclusions. The parametric bootstrap, surprisingly, really, maybe only to me, close to objective Bayes. And if you're too lazy to do objective Bayes or just want to do the bootstrap, if you just do the parametric bootstrap and don't reweight, you'll get something usually pretty close to Jeffreys or uninformative priors. And you do better with the BCA method. And when these kinds of methods apply, they're a lot faster than MCMC and don't require so much ingenious programming. Also don't require conjugate priors, which seem to have taken over the MCMC world. I should say there's nothing like, in the theory I talked today, I emphasized the Jeffreys priors, but that was just to make the talk go smoothly. The final point here says that objective Bayes analyses should be checked frequentistically. And this is a point that's been made sometimes in the Bayesian literature, but it's not honored. We get at the Annals of Applied Statistics, I get lots and lots of papers that use objective priors, and they never check frequentistically to see whether things are working out. If you believe your prior, if you have a prior you really believe, then Bayes' theorem is its own justification, and you don't need to say anything more. But if you're using a prior of convenience, it certainly seems to me that some frequentist checking is in order. Here's some references, and my thanks again to the organizers and to people who showed up, and I'll look forward to the talks and the rest of the day. So thank you.